In this session, we're going to introduce another group of external measures called entropy-based measures. We know entropy is a very useful information theory measure. Not only used in information theory, but also used in data mining, machine learning quite a lot. Entropy essentially is representing the amount of orderness of the information in all the partitions. So we still use this graph, this figure, to represent conceptually. We have ground truths represented by different color points. We have clusters represented by different ellipses. For entropy of clustering C, suppose we got R clusters. Essentially, this is the entropy of every particular cluster. Then we add all these clusters together, we get the entropy for the clustering C. Then for each cluster, actually the entropy is based on the probability of C sub I. The probability of clustering C sub I is based on the number of points in this cluster divided by the total number of points. Then entropy of partitioning T is essentially defined a similar way. Suppose we have ground truths J from 1 to K, these two K groups. Okay. So for each ground truth PT sub I, we actually can get the probability of the ground truth is defined by these P sub T sub I. Then we add all their entropies together for all the K ground truths. We get a ground truth for the whole partitioning. Then what we're interested in is the entropy of T with respect to clustering C sub I. That means we want to see how ground truths distributed within each cluster. Okay. So you probably can see this J represent the ground truths, and this I represent the really clusters. So we probably want to see such distribution so we can work out the entropy of T with respect to the cluster C sub I. Then if we want to get the conditional entropy of T with respect to whole clustering C, then we just add all these together, because this one is just for cluster C sub I, but we totally have R clusters. We add all these up proportionally, then we will get the whole conditional entropy of T with respect to the whole clustering of C. Conceptually, we can say the more of a cluster's membership are split into different partitions, the higher the conditional entropy. That's the less desirable. You probably can see if your partitions widespread into different clusters, it is no good. Okay. For perfect clustering, the conditional entropy value should be 0. The worst conditional entropy value is log K. We can use the transformation formula like this. We can transform this conditional entropy to be the joint entropy minus the clustering's entropy. Okay. So you probably can see that's the conditional formula transformation. We're not getting into detail, but you can check it. Another very useful measure used for external measure is normalized mutual information. We use a similar figure to sketch the idea. The mutual information is also defined in information theory, introduced there, but it's also very useful in machine learning and data mining. Okay. Essentially, the mutual information quantifies the amount of shared information between the clustering C and the partitioning T. So you probably can see the formula. We have R clusters, we have K ground truths. So their mutual information essentially is adding all these up together. Okay, this is a similar formula as entropy, but it's different because you probably can see this part is really this ij's probability divided by this clustering's property and partitioning's property. Okay. So that means we want to measure the dependency between the observed joint probability P sub ij of C and T and the expected joint probability of P C sub I and P T sub j under the independence assumption. Of course, if C and T are really independent, that means this one equals to this, then you probably can see this is 1, means actually when you take log, this becomes 0. Okay. Of course, in this case, this is no good because it implies these ground truths actually scatter all around different clusters. However, there's no upper bound on the mutual information, which is less desirable. That's why we need to introduce a normalized mutual information. That means we want to normalize the range from 0 to the highest one is 1. Okay. Then the value close to 1 actually indicates a good clustering. A value close to 0 means they are almost a complete random independent assignment. Okay. Then this normalized mutual information essentially is you take the mutual information, divide by the entropy of clustering, and divide it by entropy of partitioning. You product them together, take their square root, or you can transform in this way. So this is quite useful because you will know once you're clustering based on your external measure, your cluster becomes perfect if their value is very close to 1.